Welcome to Unit 5.6. Today we're going to be talking about determining concavity. Now, when your graph is concave up, that means that your y prime is increasing and your y double prime, or your second derivative, is greater than 0. And when your graph is concave down, that means that your first derivative is decreasing and your second derivative is less than 0. Concave up can be demonstrated as a positive parabola, and concave down can be demonstrated as a negative parabola. However, it's not always going to look like this. Now let's talk about points of inflection. Points of inflection is when your graph changes concavity. So just to note, when we're talking about concavity, we're always going to talk about the second derivative. You can use a first derivative graph and still find your concavity, but if you have a second derivative graph, it's usually going to be talking about concavity. So when your graph changes concavity, that means that you're either going from concave down to concave up or concave up to concave down. Let's do an example to see what this means. Given that f of x equals x to the power of 3 minus 12x, the first thing we need to do is solve for our second derivative. So to solve for our second derivative, we have to find our first derivative and then the second derivative. So first derivative, f prime of x, gives us 3x squared minus 12. And our second derivative is going to equal 6x. The 12 goes away, so it's just 6x. After finding your second derivative, all you have to do is set it equal to 0. So 0 equals 6x. You solve for x. That will give you x equals, that looks like a divided sign, x equals 0. And we will use this value to plug it into our table. Now, just like we would use the table to see if our point was increasing or decreasing, we're going to do the same. So we will have our x values on top and our sign on bottom, but this time it's going to be the sign of the second derivative since we are talking about concavity. So I'm going to put what I solved for 0, what it was at the top here. And I'm going to find intervals. So I have 0 to infinity, and I have negative infinity to 0. And just like we did before, you plug in a number that's in between the interval into our second derivative. So that's what we're going to do. A number between negative infinity and 0, we can just use negative 1. Gives us 6 and negative 1. And to find a number in between 0 and infinity, we're just going to use positive 1. 1 equals 6 times 1. This will give us a negative 6 and a positive 6. So I'm going to put negative as my sign for the interval negative infinity 0, and a positive for my sign of 0 to infinity. And the sign for 0, since we solved for 0, since we plugged in our second derivative for 0, the sign of our given value that we solved for will also be 0. So now that we've filled in our table, we can see that our concavity did change over 0, 0. So let's kind of break this down. Like I said before, when it's concave down, that means our second derivative is less than 0. So because our second derivative is a negative on the interval negative infinity to 0, that means that negative infinity to 0 is concave down. And because we said that the second derivative of x, if it is greater than 0, then it is concave up, then our interval 0 to infinity would be concave up. So we can see that over the interval, it went from concave down to concave up, which means that our concavity changes, which means we have a point of inflection. So the point of inflection would be at 0, 0, because this is when it went from a concave down to a concave up. So we determined concavity, but we also found our point of inflection, which happened to be 0, 0. And that is it. Thank you.